Hi, my name is Paritosh Mokhasi. I'm part of the kernel development team here at Wolfram Research. Today I'll be talking about mixed integer convex optimization and its various applications. Thank you. Let's get started. I'm going to talk about mixed integer convex optimization. Rob and Nina have spoken at great length about convex optimization, and so just for the benefit of anybody who didn't get a chance to attend their presentation, I just want to give you a quick overview of what convex optimization essentially means. So when we're talking about an optimization problem, we're basically talking about minimizing a certain objective, which is this f naught, subject to certain constraints. And what makes a problem convex is that these functions f naught and fi, they follow this condition, this rule. One of the important things is that when a problem gets classified as a convex problem, as Rob mentioned, the solution that you get is going to be a global solution. It's the best possible solution you're going to get. And so in the framework of this convex optimization, there are different models that come up. So you have linear optimization, you have linear fractional, quadratic, second order cone, semi-definite. And depending upon what your objective is and what your constraints are, they would fall under one of these categories. So if you have a linear objective and linear inequalities, it's a linear optimization. Okay, if it's a quadratic optimization, then your objective is quadratic, but your constraints are linear. Semi-definite, you have a linear objective, but you have these constraints which are called as linear matrix inequalities, where all these A's are essentially matrices, and it's subject to this cone, which is a semi-definite cone, which means that after you take all these matrices and combine them with these x coefficients, that resulting matrix will be symmetric positive definite. Okay. All right, so since I'm going to be talking about mixed integer, notice that the vector x, the unknown x, that we've specified for these optimization models are all real, right? What differentiates this from mixed integer is that the sum of the components of your unknown vector are going to be integers, while some are going to be real. Nothing actually changes in the objective or the constraints, right? All that is changing right now is that the domain in which the solution vector lives is going to be, sometimes it's going to be real. Some of the components are going to be real, some of them are going to be integers. But when a problem gets defined in a mixed integer, of course, a lot of it doesn't always enjoy the same status of it being able to be solved fast, because it becomes an NP-hard problem many times. So, but nonetheless, it can still be solved efficiently. I'm going to first talk about mixed integer linear optimization. Maybe I should make this a little bigger. Oh. Okay, so mixed integer linear optimization, you have linear objective and linear constraints. Okay, the way you would be specifying that in Mathematica is through our this built-in function called linear optimization, which solves specifically these kind of problems. The difference now is that you can, when you give it symbolically, you can just say that certain elements are going to be integers and some are going to be real. Or if you're giving it in the form of matrix vector forms, then you can specify that the first element is going to be real, second element is going to be integer, so on and so forth. Right? The linear optimization is, it uses branch and cut method in order to solve the integer problems. One thing I do want to mention is that linear optimization supports arbitrary precision computations, but only for real variables. When the mixed integer case comes in, it only does it in machine precision. So how would we go about solving certain problems? Here's just a very simple example. You have a linear objective, you have equality constraints and inequality constraints, and you're going to just say that we want one of the elements to be an integer, right? And that's basically all there is to it. There is no other gymnastics that needs to be done from a user's perspective. You just need to specify what elements are integers, and you're pretty much done. Okay. We do allow the users to specify this exact same problem, in this matrix vector form, because sometimes you might have some legacy code that uses this form for linear programming. So it's convenient to use it that way. So in this case, the first element is an integer, second element is real. You get the exact same problem, exact same solution, right? Okay, so really, I won't go into the details of the algorithm associated with linear optimization. Branch and cut is pretty well documented out there, so I'm going to skip that part. What I do want to talk about is how does this translate. We talked about quadratics, second-order cones, semi-definite optimization. How do we implement the mixed integer support for all these other functions? And we're going to do that by converting all of our problems into this conic optimization form. And Rob talked a great deal about conic optimization. And conic optimization is this general umbrella. So if your problem is linear, quadratic, second-order cone, semi-definite, what have you, they can all be converted into a conic optimization problem. So if we develop an algorithm or a method to solve mixed integer conic optimization problem, then that translates to us being able to solve mixed integer problems for all the other cases. Okay, so I'm going to now start focusing on conic optimization problems and what goes into for it to be able to solve mixed integer problems. Okay, so just a quick recap. You have, for a mixed integer conic optimization, you have the objective, which is linear. Your x is your unknown. You have equality constraints, and you have these conic constraints. And Nina talked about that, about the different kinds of cones that are available. And of course, some of the components are going to be real, and some of them are going to be integers. And these are the different cones that are available. Right. So if all you have in terms of a cone is a non-negative cone, then technically it's a linear optimization problem, which I can send off to linear optimization to do its own thing. If the cone contains norm cones, then it could either be a quadratic optimization or it could be a second-order cone problem, a second-order cone optimization, right? So one caveat, I should mention this because because quadratic optimization just deviates a little in terms of its objective. That quadratic objective can actually be using certain transformations can actually be converted into a second-order cone problem. Okay, so which means that even so it falls under the same category, even though we have to perform a couple of extra steps in terms of the transformation. All right, so how do we go about solving a mixed integer problem? Well, we use what is called as an outer approximation method, and this was developed by Miles Lubin, and you can look him up. His MIT thesis is available online. It's very readable. What we basically do is we take the original mixed integer problem and we break it into two subproblems. The first is a linear subproblem, which only solves. So it only takes into account the linear objective, any equality constraint that it has, and this little special inequalities. And these inequalities actually come from the conic subproblem. Okay. So for now, I'll explain what this beta is in just a minute. But for now, assume that this beta is available. So you have a bunch of these half spaces that are available to you, and you go ahead and solve this linear subproblem. Okay, once you solve this linear subproblem, you then extract some of the components that are actually integers, and you substitute them back into your conic relaxed subproblem. So the integer values are substituted back into there, so that implicit integer constraint is removed, and you solve that problem. Once you solve that problem, you then extract the dual associated with all these conic constraints, and from that dual you compute this half space, this beta. That gives you So from there, once the beta is constructed, you go back, solve the linear subproblem, get the integer value, substitute back in. You get a new half space, you substitute that back in, iterate till convergence. That's basically what we do. Okay. In case that was not super obvious clear, I'm going to show you an example because I'm pretty sure it wasn't clear. All right, let's do a simple example. All right, that's your original conic optimization problem. Okay, I'm going to break down the steps. Everything that I just explained to you, I'm going to try to show it to you in a graphical way. The first thing we're going to do is we're going to solve a relaxed conic problem. Okay, notice that x is not an integer here. Nothing has been specified. Okay, I'm going to extract the primal and the dual from it. If you want to see the numbers, let's do that. Okay. So now that we've taken out the dual, now we have to form that beta, that half plane that I mentioned. And the way we do that is we use the dual cone associated with the constraint. And so that's the H plane is what I've computed. So what does it look like? Of course. Okay, that's what it looks like. So this semicircle thing that you're seeing, that's your feasible region in which you're supposed to carry out your optimization problem. And the half space plane is this line with everything below it. Okay. So now that we've computed this half space plane, we plug that into our linear optimization problem, which you see right here. I'll just pull that up. And you specify that the x is an integer. Okay. That gives you, and then you extract the integer value from it. Now that you know a first guess of what the integer value is, you plug that back into your original conic optimization problem, solve again, and you get a new result. Okay? And now you form another hyperplane. And that's your second hyperplane. So the first one was that horizontal. The second one is that more diagonal one, right? Now you have two planes. You substitute both of them back into your linear optimization problem. Where'd it go? And you get back a new value. Let's see if I can. There. Get back a new value, -1, which is actually the solution that we got in the first place, right? So in this case, the linear optimization actually gives you an upper bound on your primal minimum value, and your conic subproblem gives you a lower bound. And when the two of them match up, that's when convergence is achieved and you stop your iteration. This is exactly what we are doing behind the scenes. A little bit more efficiently, obviously, but you get the idea. So that's basically our outer approximation algorithm. I should also mention that Nina pointed this out, that Mosaic also would do that. It uses a completely different mechanism to do it. So if you have a Mosaic license down the line, you could use that. All right. So what exactly can we do with mixed integer? I mean, it's all well and good that we can solve this, but what mixed integer allows you to do is opens up a whole area of modeling that would ideally not be accessible. So for example, if you want to, I've given a whole bunch of lists here. I'll just go through a few just to show you what kind of tricks can be done. Let's say that you have a variable, you want it either to be 0 or you want it to lie within a certain bound. Well, you can do that by introducing a binary variable which takes on only a value of 0 and 1 and is forced to be an integer, and you multiply that with the bounds. So when z becomes 0, x is forced to be 0, and when z becomes 1, then it will lie between this one. This is typically won't be possible if you were just do regular conic problem, because it's not a continuous, the space is not continuous. Let's focus on the third one, doing OR statements. This becomes extremely handy when you are doing things like path planning, avoiding, when you're doing optimization of a car moving through obstacles, for example. These kind of OR statements become quite important. You either want one constraint to be satisfied or the other, but not both. Okay? In such a case, you again introduce a binary variable, and you introduce this large value called m. By the way, these methods wherein you start seeing this capital M all over the place, these are called big M methods, which is similar to what you would do when you're doing simplex programming as well, right? So m is a large positive value, and in this case, if z is 0, then the first constraint is satisfied. If z is 1, then the second constraint is satisfied. Another way of looking at it, if you stare at it long enough, one of the constraints becomes redundant, right? Depending upon which variable gets switched, one of the constraints becomes redundant. So there are multiple different formulations and tips and tricks that can be used to enhance the scope of the problems you can solve using the convex optimization framework. Okay, enough theory. Let's jump into some application examples. Sudoku. Let's solve the Sudoku problem. Okay, this is a typically hard Sudoku problem because, and I think it got a lot of attention because the number of knowns is quite small. We're going to solve this using the mixed integer approach, and the way we're going to do that is each element in our Sudoku board is going to be represented by a 9-dimensional binary vector, right? So it's a 9-dimensional vector. It's going to each element within that vector is going to be either 0 or 1. And the way what we're going to do is whatever element becomes non-zero, that is the number that will get assigned to this unknown value, okay? So for example, we know this is 5, so there's a 9-dimensional vector associated with this block, and the 5th element there is 1, everything else is 0, okay? So that's our base. Now that we have that in place, so let's go ahead and, these are all very fast, so I'm going to go ahead and, so that's the first constraint, right? Now, the rules of Sudoku say the rows and the columns should all, no number should be repeated, which means that from a binary vector standpoint, if I were to add any row or any column, they should all become a vector of 1s, right? So that's what we're going to do. That's our row we're going to add a row constraint, a column constraint, and Sudoku has a third rule which says that the 3x3 blocks should also be should not have any repeated elements in them. And that's our third constraint. Now we're going to collect all these variables, and we're going to now specify with the constraints that were given to us, all these known digits. So we substitute those in, and we solve our linear optimization problem. Let me just go ahead and make this so that you can see it better. So we solve that, and oops. And that's our result. And it happens quite quickly, right? In the documentation, we've actually taken it a step forward, and we have actually shown you how to develop your own Sudoku solvers. So you can do the inverse problem. The process is so fast that you can actually run it so quickly that you can actually generate your own unknown Sudoku boards. So have fun with that. All right, a second example, which is a path planning around obstacle. Let's say that I have an object, just some random object, right? What I would like to do is, there's going to be a start point and an end point, and I want to find a path that goes from the start point to the end point without going through this object, okay? So the first thing I'm going to do is this, we can extract the half spaces associated with this mesh, with this object, because it's a convex object. We can extract the linear inequality constraints associated with it. We're going to specify a start and an end point. There we have it, right? We're going to start at the bottom, and we're going to try and work our way top, right? Obviously, it can't go through a straight line, so we have to find a path around it. So what we're going to do is we'll discretize the path by a number of points, right? So we'll say pi are the number of intermediate points in between, and we're going to use 10 points. So between the start and the end, there are going to be 10 points, or 8 points. 9th and the 10th are going to be the edges. And what we want to do is we want to minimize the distance between the subsequent points, right? So that is equivalent to minimizing the path distance. And using this epigraph transformation, we are going to convert this problem into a quadratic optimization problem. So that's our objective. Our objective here is sum of ti dot ti. So that becomes your quadratic objective. Okay. We now specify our endpoints, which is the start and the end, right? And now what we are also going to give it some additional things to make our lives a little easier, which is to say that make sure that no 2 points are too close to each other. Otherwise, they might get grouped together. You might not get a good result. So you want to separate those points out and evenly space them through the path. All right. So here's the actual trick. The formatting got a little messed up, but the actual thing is, if I go back here, what we wanted to do was to formulate a path, which means that all those discrete points from the start to the end, none of them should lie inside this, right? And the condition that is required for any point to lie inside this is that the linear matrix inequality, that ax dot b, right, this a dot pi dot b should all be greater than or equal to 0. If any one of those conditions get violated, it means that the point is outside the domain. And that's exactly the constraint we want to put in. Okay? And the way we do that is, again, using this binary variables. So for each one of your points, discrete points, we are going to assign a binary variable. And we're going to say that the total of those binary variables should be less than m minus 1, where m is the length of your linear inequalities in there. So we've chosen that m value to be 10 here so that it's large enough, but it's not too large that things go all haywire. There's a little bit of, you'd have to, m is a user-defined variable, so beware, you'll have to play around with it a little bit. I'm going to solve this quadratic optimization problem. I'm going to let it takes a few seconds for it to get the result, because it converts into a conic problem, solves it, and that solution process actually takes a bit of time. And there's your result, and there's your path. Now, Rob and I have butted heads on this graph over and over. Rob says that this is not mathematically correct. As an engineer, I say that's correct. And it's got to do with the fact that it's passing through this point here. But nonetheless, you can see a trend happening. If you increase more points, it's going to, this gap will go on reducing, and eventually it'll come. The other way you would do a path planning problem like this is you take this and you make it slightly bigger. And you make it slightly bigger and run the same problem, and then you shrink it back. It'll avoid that obstacle. That's one way to do it. Right. Okay. So one more example, I guess, which is your graph coloring problem, which is a very famous problem. So you have all these nodes connected by a graph, and how many colors does it take to color that graph so that no 2 adjacent nodes that are connected to each other will have the same color. So this is a graph coloring problem. I'll start with 6 colors. I'll generate a random graph. And the objective is to start putting colors on each one of them so that there's no 2 adjacent nodes have the same color. So I'm going to extract the adjacency matrix from it. This is the condition that says that no 2 of them are going to be of the same color, and we are going to use 2 binary variables in order to set up our modeling problem. Okay, so the same color constraint says that no 2 nodes will be the same, and then we say that if one of the nodes is assigned a color, then that color will be part of our final set of colors. We specify our binary variables. In this case, notice that X is a matrix, and it's got a dimension similar, which is the same as our binary matrix, our adjacency matrix. And Y is a binary vector that's associated with the number of colors I initially decided to use. And we run the problem. This turns out to be a linear optimization problem. And linear optimization is generally pretty good. It's like I'm over the limit. And we solve that. Here's the total number of colors, which turns out to be what you need, and there's your result. Okay. So I've just about run out of time here. So if you have any questions, please feel free to ask. You have a question? Great. I'm glad you guys enjoyed it.